All right, so good morning, everybody. And first, thank you for coming to the third seminar for this semester. So today we are very happy to have Professor Dingwen Tao as our speaker today. So he is an associate professor at the Indiana University, Bloomington, where he directs the high performance data analytics and computing lab. So he received his PhD in computer science from University of California, Riverside, and a bachelor degree in mathematics from University of Science and Technology of China. So he is the recipient of various awards, so including the NSF Career Award, Amazon Research Award, Mentor Research Award, R&D 100 Awards winner, and IEEE Computer Society TC HPC Early Career Researchers for Excellence in High Performance Computing, and NSF CRI Award and IEEE Cluster Best Paper Award. So he's serving as an associate editor of IEEE Transactions on Parallel and Distributed Systems. So he was also a program committee member for major HPC venues such as supercomputing, HPDC, ICS, IPDPS, etc. So he is a senior member of IEEE and ACM. Okay, so let's welcome our speaker.
Thank you, Professor Tao, for introduction. I'm very happy and honored to give a talk today. So I will talk a little bit about our recent research on high performance computing and machine learning system, especially using efficient data management approach to improve the system and application efficiency and performance. So first, let me talk about some system issues in HPC system. Probably not everyone here are very familiar with the HPC system, right? Or supercomputing. So a general background, so if you have a very large and complex problem for computing, you have resources like supercomputers, or we can call it HPC system, right, to help you with those complex problems. And those systems are very powerful, kind of a giant, consume a lot of electricity, power, with a very high-end hardware such as a GPU, CPU, high-end networking. But if you take a look at those machine built by building United States, you would find the performance. Let's say, if I can have a laser here, right? So this is a year of the building the machine, and you can. See my laser? Probably not. Give me one second. Let me share the whole screen for you. Seems like my Zoom is just try. Okay, good. Yeah, thank you. Okay. So if you take a look at this table, you will find the performance of the system increase a lot, right? So from 1 petaflops per second to 100 petaflops per second. Now we have an exascale machine. Exascale is a 10 to 18 floating point operation per second, right? But if you pay attention to the other metrics or measurement of the system, you would find the memory size and the storage bandwidth versus the peak performance is kind of increasing, right? So which means that the gap between the performance and the storage system or IO bandwidth is increasing, right? Or in other words, like let's say computer power is growing so fast, but the storage capacity and bandwidth is developing relatively slowly, right? And if you take a look from application perspective, there is some delay. So we have like a different type of the application. For example, we have like cosmology simulation, which is to help scientists to understand how the universe forms, right? And how the universe will change in the future. If you simulate those type of application, you need 20 petabytes of the storage or data, right? And which could easily consume all of the storage space in the system, right? And if you consider like climate simulation, more and more money has been spent in building the hardware for saving the data, right? And if you take a look at the old supercomputers, IO bandwidth is only 1 terabit BPS per second, right? So you need to spend hours to save the data. And if you take a look at some like high energy, I think it because networking is not stable, seems like. Yeah. So let's keep disconnecting from Zoom. So Amo, do you think it's possible we can?
Yes, we can try to
connect to the machine or not through the Wi-Fi? I don't know. Simply choose here. Oh, that's good. I can create room. Okay, that's good. Thank you. Is it better? Yeah, I think it's better. It's more like a real time, right? We care about the performance. So yeah, let's say if you are taking a look at the high energy physics experiment, right? They also the experiment also generating a lot of data for let's say like 100 of petabytes of the data. And if you save those data from the those like beamline facility to the real supercomputers, right? You need to spend also days to transmit the data. So after we discussing with all those like application people, we conclude some solution like, we conclude some like observation like those applications really need to have a highly efficient solution to manage those data. Sometimes we need to reduce the data size with different numbers. For example, like a cosmology simulation, climate simulation, we would like, as a domain scientist would like to reduce the data size by 10 times. And for those like beam lines, for those like experiments, if we can achieve hundreds of times data reduction, that would be good for them to do their like scientific research. Right, and if we take a look at those like system like architecture, right, we can identify that now a lot of systems have different accelerators, such as the GPU, such like FPGA, such like some smart NIC, and if you want to move the data between those hardwares, it also costs time, right? So that's why people are saying that now, if you want to have a good performance for your system, for your hardware, for your application, you should do a better data management or moving the data more carefully, right? This is another motivation. So by combining all those above factors, we have some like idea to reduce the data size significantly, but during meantime, we have to guarantee the users or application have a good information, right? So then we come up with like a solution called lossy compression. And maybe you are not that unfamiliar with lossy compression, because if you are using JPEG, if you are using video like MPEG, right? Those like a format, they are automatically has some compression capability there, right? But what's the difference between our traditional image compression or like a video compression versus like our scientific data compression, right? In my previous example, we deal with all the scientific data, right? So the challenge here is like, first, the data for floating point are mostly for the scientific data are mostly the floating point data, right? Floating point data is not like an integer, it's not an image right? They are like a more random. They are more like if you take a look at the right corner figure, right, you will find like those floating point data is like a kind of a random noise, right? So you have some challenge to identify some patterns in the data, right? This is the first challenge. The second challenge is that we are not doing the visual quality assessment. Scientists need to do some scientific discovery. For example, they need to analyze the data for energy purpose if they are doing the molecular dynamics or for some like scientific research, right? Or for climate, they have to guarantee like this data are still follow some physics model. So the fifth condition, it must satisfy some post-analysis requirement, right? You cannot just based on the visual quality, but you also need to guarantee they are like a post-analysis. And also, the compressor needs to provide a good controllability of the data set. For example, you can control the data for per point, or you can control the data based on L2 norm, or you want to provide some like a fixed rate compression, right? For example, the data originally is 100 megabytes. After compression, it's about 50 megabytes, right? You have to fix the ratio as a 2, right? So you have different requirement for a compressor. So during the past almost 7 to 8 years, I have been collaborating with national labs, Department of Energy, national labs, and we have developed a compression software or framework called SC, lossy compression. It's kind of like a prediction-based compression framework for scientific data. It has a strict control of the global upper bound of the compression error. And we have implemented that on the CPU, GPU, FPGA, different architecture. And for user easy use purpose, we have integrate those software into some IO libraries. If you are not familiar, what is the IO library? It's kind of like when you write a program, you have to call some software to write your data or read your data, right? If you are familiar with the Python or with the PyTorch or those software, you know that they are the data loader or data writer, right? So those is some IO libraries. We have to integrate our software into those libraries. So for easy use purpose, right? So this is a high level idea of what we are doing for efficient data management or data compression, right? So here is one slide to talk about our main idea or main strategy here. So actually, the reason we call it a framework because it has different stages. For example, let's say we have a prediction stage, we have the quantization stage, we have the encoding stage, right? And the input is the original data with some parameter, for example, how much error you want to lose, what is the accuracy of the data you want to control, right? And the input data could be higher dimensional data set, 2D, 3D, 4D, even 5D data set. Could be tensor, could be matrix, right? And for this framework, as I mentioned, we have different stages. And the first stage is kind of like we want to reduce the data correlation by using some like a prediction strategy. And the left corner is showing a very simple predictor, right? So if you want to, predict the value of this point, you have the neighboring point information or values, and you can build some prediction model or function, right? Linear function, nonlinear function, even a neural network, right? To predict this point. And based on the prediction of this point, you can have the difference between the real value and the predicted value. And based on the difference, you build some like quantization code, right? So quantization means like you've changed from floating point to integer or to like a low bit precision, right? And then we identify that those quantization code has some like a very good feature for lossless encoding, such like Huffman encoding, such like other lossless encoding technique. So actually this is the original framework. Why I call it original, I will expand that. We have some more advanced framework now or in development, but this is our original framework. And the reason we call it a framework because you can even change the different stage technique. Let's say if you don't want to use a default Lorenzo predictor, you can change to, as I mentioned, neural network predictor, right? So if you don't want to use a linear quantization, you can use other quantization technique. And for encoding, we can use a traditional Huffman encoding. Maybe some of you know that, right? This is a very traditional techniques in the coding theory, right? You can use maybe some advanced technique, for example, this standard developed by Facebook, right? And this slide showing that our framework or software actually has some like good achievements. We got funding from National Lab DOE for ECP project, although ECP is ending, but we are trying to get some new funding from DOE, and we get actually this number for NSF needs to be updated because we recently get $3 million from NSF to build a large community, and we get some funding from like companies because company needs to use our software to help them to run some like problem. Let me try to explain that. So our use case, we can reduce the storage footprint, definitely, right? When you compress data, you can save the storage. And you can also accelerate the IO and the communication, right? Because when you reduce the data, you can easily transmit the data, right? I haven't tried to apply those things to IoT or wireless, but I believe it can help maybe for IoT scenario. I know some people are using our software to apply to maybe smart devices, right? To between cloud and the device to reduce the communication latency, right? And also we can accelerating visualization because we don't need to save the data to the offline disk. We can do in situ visualization. We have reduced the streaming intensity. We can run in larger problem. For example, there is a team from China. They're trying to run like a seismic simulation, but they are like a problem is super large. So they are using our software to reduce the resolution and running large scale to help them to identify some seismic simulation problem, right? And also for AI cases, we can use our software to do model compression, right? You reduce the model size, and the model can be easily deployed on some like smart devices, like camera, or like a smartwatch, or like any like intelligent end device, right? And you can accelerate a large scale DN training. I will have a paper published in VLDB talking about how we can use a compression to accelerate the DN training, and we reduce the memory consumption. We can accelerate distributed training. So those are like our actively invested use cases, and we are trying to find more applications. And specifically for Aramco, it's like a oil and gas company. So they are trying to use our compression technique to help them to run their like simulation faster because they have to do the field experiment in the real time, and based on the feedback, they need to run the simulation. So it's really need to be very fast and efficient. So compression can help them to do that. So we get some funding from them. Yeah, I think I should quickly skip these slides because almost everyone is talking about large language model, right? And why AI also needed to have compression or like data management. One scenario is like a model is becoming large, right? Everyone is talking about that. This is kind of like old figure, but now the LLM, right, large language model is even larger, right? And also the memory consumption for GPU is kind of challenging because you can see like the GPU memory size increased from 10 gigabytes to 20 gigabytes to 40, now it's 80, right? But it's very hard to further increase the GPU memory size because GPU memory is very expensive. It's not like CPU DRAM, right? It's like a HPM, right? HPM, high memory bandwidth memory. So it's kind of expensive to have larger memory size. So how can we use compression to reduce the memory consumption, as I mentioned, right? We have some work there. I will talk about those work in the following slides, but I just want to give you some heads up about the motivation why data management is important to AI and how compression could help. Right, and here I list some of our projects about machine learning and HPC system for using or for optimizing or for adapting our compression framework. Yeah, so first one is my career proposal. I want to build like an effective, usable, performant, and scalable data reduction framework for HPC systems, specific HPC system. And second and third is like a cyber infrastructure program. We have to collaborate with a domain scientist to optimize our compressor to their use cases. Some people need a very fast compression speed. Some people need a high throughput or high ratio. So we have to customize our software to them, right? And the last project about the machine learning, as I mentioned, one project is kind of like already ended project CII 5 years ago when I started as my assistant professor. So we're trying to use the compression to accelerate deep learning application, right? The last project actually was funded by Meta. So they have a very, I will talk about this project using some slides, but the key idea is that when they're trying to recommend some news to users, right, they need to train a recommendation model. Actually, in those recommendation model, the communication is a major bottleneck. each round of training the model need to spend more than 40 to 50% of the time for communication. So we are trying to use compression to accelerate the communication. So this one slide is about our recent funded project from NSF. It's a CSSI project. It's a cyber infrastructure for innovative science research project, right? It's collaborative between University of Chicago, Indiana University, Ohio State, and Florida State University. So this project actually is a software development project. It's not kind of like a research project, but we have to put our previously all the software, our users, our communities together, and to create a very easy use framework for domain scientists. Because as I mentioned, if in the future we find some new use cases, we have to customize our software to them. That spend a lot of time. Sometimes the time cycle is 1 year, 2 years. Now we are trying to automate all those things, right? If you give me a data set, you give me some requirement, you give me some like a constraint, and you are trying to generate some Python interface, we can use this framework to do that at the same time, right? And we provide you the high-level Python interface, and you can call the backend CPU, multi-threading, GPU code efficiently, and we can satisfy your requirement. For example, you don't really want the speed to be lower than 40 gigabytes per second, right? Then we can satisfy your requirement. And we have been collaborating with different domain people because NSF really care about how the software will impact the real science, right? So we have collaborated with or domain people. For example, we collaborate with the cosmology people, climate people, as I mentioned in the motivation slides, and the seismology people, and the plasma physics people, material molecular dynamics people, material science people from experimental science, and the quantum circuit simulation people, and the combustion people, right? We're trying to cover as many as possible. Eventually, we want to build a community. And last week, I just attended this project by semi-annual meeting, right? And we chat with all those scientists and we get their feedback, and we will put this feedback into our next project execution. This is kind of our new project. And one like slide, not to show off, but just like to give you some idea, some publications we have done with my students, and I classify those like papers into 3 categories. One is just a lossless data compression techniques. It's kind of like a fundamental research, right? And we published the paper in some top venue, and we designed some generic framework, as I mentioned, right? SE framework. And now we are trying to customize for the different applications. So we have the domain specific paper, and we also have some GPU FPGA acceleration, because I will mention that why we have to give user very good GPU code, right? Because they are using GPU a lot, right? And then we are also trying to integrate our solution, right, into the different scenario communication, I/O memory management, right? So we publish those type of paper in database, in the architecture, in the system I/O in these venues, right? And finally, we have some papers in the deep learning system, not all about compression. Sometimes it's just about some pruning. But pruning, you can take pruning as a compression as well, and the hardware software co-design in some like a hardware FPL, those like FPGA conference, right? So those are my research or publication portfolio, and I think my principle is like we hope like in each area we have been working on the project, we could have like some publication to disseminate our research, right? As I mentioned, general framework, domain specific, hardware acceleration, and some like use cases. So let me, I spend maybe half hour, 25 minutes to talk about some like a high level thing, and I can select the 1 or 2, not 1 or 2, but maybe 3, right? Let's say 3 papers from these publications, and give you some more like a concrete ideas what we are doing in terms of research and some evaluations, right? The first work I want to talk about is our GPU-based lossy compression, because I just gave a very high-level overview of our compression framework, right? Prediction, quantization, encoding, blah, 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 and applied to the application, right? But the problem is that those framework is only algorithm, right? When you try to put algorithm into real system or application, you have to care about the performance, the integration, the hardware, right? And this work actually was the first work of the GPU compressor, and sometimes I claim it as the first GPU-based lossy compression in the world, right? And can control the error and can run on the CUDA GPUs. I have some evaluation I can show you. But one slide to quickly talk about why we want to do GPU and what is the challenge in porting the algorithm to GPU, right? So if you are not very familiar with GPU, I can give you some background. So GPU, I think now it's becoming more and more famous, right? Because AI people is using GPU every day, everywhere, right? But the GPU traditionally is not invented for AI. I could say like it's for graphics or visualization, right? And then high-performance computing, and now it's for AI. The reason is like AI, GPU is really good at calculating floating point operation, and also it's very good at compute things in highly parallel way, right? For example, you have vector plus vector, matrix times matrix. GPU is very good at it because each instruction will be executed on different data. Maybe you know that SIMD or right. So those like a concept. GPU is very good at it, but the challenge is like not all the algorithm can be adapted to this style, right? You give it one instruction and calculate everything in the same way, right? So we have to adapt our software to the GPU architecture, and then give you another, like on the other hand, give you some reason why we need to develop our software to GPU. Maybe you can say like, okay, you just use the GPU data and then use CPU to do compression. It's not good because when GPU generate the data, you have to deal with the data, process the data, save the data immediately. Otherwise, you have to move the data from GPU to CPU. Then GPU, CPU bandwidth will become the problem. Okay, let's say like a GPU, CPU bandwidth is only about 30 gigabytes per second, right? GPU throughput is like terabytes of second, right? So then you have the problem because you move the data between CPU and GPU. Most of the time you are waiting for data. You are not doing computations, right? So the idea is like when GPU generates data, let's compress that, let's process that, rather than giving CPU to do that. Okay, and yeah, I explained the reason why we use GPU and the challenge to use GPU, and specific to this algorithm. Or previously, CPU algorithm is like we are doing the serial processing, right? We process. Still remember, I say like we predict this point, and we quantize the difference, and we encode that, and then we move to the next point, right? This is a sequential way. So GPU is not good at the sequential processing, or it's not using sequential way. Otherwise, GPU power is not utilized, right? So you have to do every time, every spatial points at the same time. But the algorithm has some dependency. So the first problem we need to solve is to remove the data dependency in the algorithm. Fortunately, we have invented some algorithm. Right? I don't really want to go into the detail, but the idea is that we can doing some two-stage quantization. We can do pre-quantization to convert the floating point data to integer. And based on this integer, we can do the quantization at the same time to all the data points. And based on the, do the prediction to all the data points. And based on the predicted value, we can do the second round of quantization. And mathematically, we prove that this outcome of this approach is exactly the same as original CPU version code, right? This is some proof. I shouldn't go into that. And after that, the idea is like you will get the quantization code, right? You will get the code for half-man encoding, right? And we still find some challenge because if you are using GPU to do half-man encoding, the problem is like you have to go through the half-man tree, and the half-man tree is kind of random if you have any idea, right? So if you ask each thread to go through the half-man tree, some half-man tree is the leaf is very deep, some leaf is very shallow, right? So then you will face some challenges. So those are the challenges. I'm not going to treat too much. And then based on these challenges, we have done some work. For example, we've revisiting the half-man coding on the modern GPU architecture published in IPDBS. And also we're optimizing half-man decoding on the GPUs, right? So actually these are the two stages, but eventually we published two papers because the different coding and the decoding they use different kind of algorithms. And then we also do some like performance optimization to tune the number of threads to achieve good performance, blah, blah, blah. I'm not going to those details. I want to show more like high level things to you. If you take a look at this figure, I will give you some idea how fast our compression is, right? And we evaluate on some like old version of GPU V100, or we also evaluate on the A100 GPU, and we evaluate on the different type of the data set, cosmology data set, climate data set, hurricane data set, cosmology data set, and some like quantum chemistry data set, right? And you would find that our compression throughput is about 50 to 80 or 90, right, gigabytes per second. And compared to the original CPU version, is only about hundreds of megabytes, right? We increased several magnitudes. And is this enough? So maybe you will ask this question, right? So compared to the CPU and the GPU data transfer, it's, as I mentioned, it's about 30 gigabytes per second. 90 gigabytes or 80 gigabytes, I think it's good, right? So if you consider when you move the data to CPU to compress, compared to directly compress on the GPU, right? 90 gigabytes, I think is good. But some users still hope like have hundreds of gigabytes per second, right? We are still working on that. But this is a trade-off. If you want to have very good high quality, high ratio, sometimes the throughput is not good, right? It's maybe only about 30 or 40 gigabytes. But if you need hundreds of gigabytes, we have to change the algorithm slightly. Yes, I just give you some idea. If you really want to have some compressor, have hundreds of gigabytes or tens of gigabytes per second, maybe you can consider our solution, right? And our solution is kind of, I think it's kind of state of art. So this work, actually, the next work, the first work I'm talking about is the GPU compression, right? The second work I'm talking about is the work we published in supercomputing in 2022. We are trying to leverage the compression to accelerate the parallel I/O, right? And the first is a motivation, right? Why you want to accelerate the I/O, right? If you understand some scientific simulation, as I mentioned, it's kind of like time step based computation, and each step you need to write the data to the file system, to the storage system, right? If the data is really large, as I mentioned, it will delay your overall computation or performance, right? And also, as I mentioned, storage is limited. So if you write a lot of data to the storage system, the storage system could be crashed or corrupted, or maybe the system administrator just stop your application, right? So you have to solve some storage problem and I/O bandwidth. This is some general motivation. I have already explained that. And specifically for this work, you may think about, okay, why you need to integrate compression into the parallel I/O library, right? You can generate just when you try to write the data, you make a compression and you write the compressed data to the disk. That's easy, right? That's the solution people are traditionally use, right? But our idea is like, this is not optimal. We can identify some optimization opportunity here. The limitation of traditionally parallel HDFI I/O with compression is compression and I/O, they are sequential, right? They are not well overlapped. They are not well integrated, right? And because of the compression size is not pre-known, so we cannot easily set up some configuration, right, to enable high efficient parallel. I just give you some example. Maybe this example is the kind of fun and give you some idea. So what is our optimization, right? Not going too much in the detail, but the figure sometimes is the best way to prove the idea, right? So take a look at there is a 1, 2, 3, 4 solutions, right? This is not compression. You just write a file, so you can see because the file is large. So you have a 1, 2, 3, 4, 5. You have 5 processes, right, to write the data simultaneously, and some process finish earlier, some process finish later. So the overall time is depend on the latest one, right? You can see this from here. So this is timeline, right? So here to there, this is the overall execution time. And this is the I/O time with compression. So you have 5 processes to compress data. Black is compression, right? You compress the data, and the last process finish the compression. You start writing the data, right? And then this is the next time step. This is the compression. This is the next time step of I/O, right? You can see, okay, compression IO, right? They are sequential. There is no overlap. There is no optimization. Okay, and this third and fourth solution is our solution, right? You can see like if we can enable compression and IO at the same time, you can first compress the data and then starting writing the data. And during meantime, you can compress the second round of the data, right? And then you finish that, you write the data, right? But why this is cannot be done previously? This is because when you want to enable this pink bar for writing, you have to know the size of this data. But this size of the data, because of compression, you don't know the size before it's finished, right? Not like a no compression solution. No compression solution, you know how large is the data size. But with the compression, you never know the size before you finish the compression, right? So to solve this problem, we develop a prediction model. We can predict the size after compression so that we can enable the IO overlapping with the compression based on our prediction result, which we call it offset, right? When you try to do parallel IO, you have to set up the offset. Offset is the size of the compressed data. We predict that, and then we enable those things. But another challenge is that this size, based on our prediction, is not always 100% accurate, right? Sometimes we predict the size a little bit smaller. The actual compressed size is larger. Then you will face some problem is you will have some overflow, right? You reserve this size for writing the data, but actually the data is larger. So you have to handle those overflow cases. Then we design some system mechanism to handle those overlap things, right? So this slide, I really like this figure because this figure can demonstrate our idea, and I don't need to go into too much complicated things, right? And then one slide to show you how performance we can improve. So compared to the original no compression solution, right? With compression, it can increase the IO performance or reduce the IO time by 1.8 something, right, times. And with our overlapping solution, we can further reduce the time by 1.8 times. Okay, there is one optimization I haven't described. So I described this, right? So how about that, right? How about this? This is a compression scheduling optimization because different data fields have the different, so you can see I mentioned this is the one time step, this is the second time step, right? And this is the one time step, the one field, the second field, third field, fifth, fourth field, fifth field, right? And if we can reorder some of the fields for compression, we can achieve better overlapping efficiency, right? This is kind of like a scheduling thing. So if you have some like experience doing like a computer system scheduling thing, right? This is very similar. You can schedule the task to enable better overlapping. And after compression scheduling, right, we can achieve better overlapping and better like performance, right? This is our second optimization. So overall, we can achieve almost 3 times improvement, and we can we only introduce a 1.5 storage overhead. I just explained why there is an overhead because we have to handle some overflow cases, right? So if we handle those overflow cases, we have to reserve some space for those data. So we have a small overhead, but we improve the performance. Okay. Yeah, we evaluate on the different scales. So this is our traditional experimental strategy, right? We evaluate different number of processes. We evaluate different supercomputer system. We evaluate on different type of the data set, and demonstrate. You can see like we evaluate on like 2 large scale real data set. Yeah, so this is the idea of that, and this is actually the poster, not a full slide, but it's about our. I presented in the ASFPI meeting. So just to let you know that we further improve those scheduling based on some like traditional system scheduling approach, right? Because we think like this scheduling is not the perfect. We still have room to improve that. Yeah, we further improve that to conceal the compression and the IO overhead through the task scheduling. We exploit, I think it's 4, maybe 7 or 8 different scheduling policy. And based on this scheduling policy, we derive like the the optimal scheduling policy. Not going to the detail, but just letting you know that the research is never ended, right? So even you have some like scheduling to reduce the overhead, but you can do better. So but anyway, I don't have the full slide because EuroSys 24 is not, we're still preparing that. Okay, so I'm not sure I'm going to this because I still want to touch a little bit on the machine learning, but this thing, maybe if you I talked to you this morning, right? So we also have some solution to accelerate the AMR, adaptive mesh refinement applications. So just give me 2 minutes, I can quickly describe what we are doing in this work. So for AMR application, it's kind of like different regions have the different resolution for computation and for storage, right? You don't need to spend the computation effort or storage effort to all the points, to all the meshes, right? So you spend more time or more data or more computation on the regions you are really interested, but some background you don't need to care about that, right? So the reason to use this AMR strategy for domain people or application code is like they want to save time, they want to save computation time, they want to save the storage, right? But even with those AMR strategy, data is still large, right? For example, let's say 2.8 terabytes per time step, and you will have hundreds or thousands of time steps. Right, you see how large the data is, right? And so the previous solution is try to dump the data to the disk and try to analyze the AMR data and then try to compress that, but the efficiency is kind of low, right? And and also, for example, AMRX framework, they have naturally built the compression solution, but it's also very low efficient, right? Because they just treat all the AMR data as a 1D data set. They do not leverage the high dimensional information. So we are trying to improve that, okay? And by the way, this work was published in last year's supercomputing. So our goal is to utilize the in-situ compression to improve both IO efficiency and the compression performance for AMR application. Okay, I'm not going to the detail, but the high level idea is that we want to leverage because as I mentioned, AMR is adaptive mesh refinement. So it has a fine level, coarse level. It have like, for example, like 3 level. One is the finest level, second is the middle level, last is the coarse level. Then different level, actually, they have some data correlation, right? So we can leverage those data collaboration to better serve the data compression, and we can do better compression. Okay, that is the basic idea. And then we revise the software algorithm, we integrate into AMRX framework, we evaluate with a large scale application, blah, 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 those like a publication strategy, right? But the key idea is compared with a traditional AMR data compression, we have a good pre-processing, we have a better data decorrelation, encoding approach, and also we need to kind of revise the IO software HDF5 filter, right? And my goal and my student is kind of working with the MRX team. We hope to replace its originally built IO software. At least we can add one more plugin, and MRX people can naturally use that for their applications. And here are some results, right? We run on I think we run on different applications. Let's say we run on WARPX. WARPX is actually the Golden Bear Prize winning application using the MX, and the next is a cosmology simulation with different scale. You can see the blue bar actually is not blue bar, it's our bar is actually lower than the original approach, even we introduce some pre-processing time. But anyway, I'm not going to this. I just give you some idea what we are doing for this work is a little bit more scientific computing thing and with real application. This is some visualization demonstrate like even with our compression, our quality are improved, right? This is original data for the WARPX simulation. And this is original AMR framework's built-in compression. You can see there's some artifacts, right? To affect you to understand this scientific result. So they shouldn't be this like this area or region, right? And after our improvement, you can see it's almost the same as the original data, right? But we provide better ratio, we provide higher IO efficiency. Okay, so this is it. Okay, yeah, I will spend maybe another 10 minutes. I know everyone is kind of hungry for lunch, right? I will try to close my talk with some like machine learning works. So this work actually was published in VLDB 2022. As I mentioned, compression, scientific compression or floating point data compression is not only useful for scientific computation for HPC, right? But also useful for machine learning, right? But what is it? How we use that, right? So give you some idea if you're not very familiar with machine learning, but maybe most of you know that, right? So if you are not training a neural network, or training a CN, training even a large language model, right? So you are trying to have a forward propagation and backward propagation, right? Forward is trying to pass the neural network, backward is trying to update the gradient, update the model, right? And the challenge here to for performance purpose or for the hardware reason is like you during this like a layer by layer neural network computation, you will generate a lot of intermediate data because this intermediate data needs to be used in the backward propagation to update the gradient, right? This is kind of like the workflow, computation workflow for this workflow, right? For the neural network, right? You pass a convolution generates a lot of activation data, and then you pass the next layer, next layer, and in the backward propagation, you use this activation data to calculate the gradient and then update the weights, right? This is the framework. And our idea is kind of straightforward. We are trying to compress the intermediate data and use less memory space to host this data. Then you can train larger models. You can train more data. You can increase the throughput, right? But the trade-off is like when you compress the data, you have to decompress the data, right? But there is another story. We're trying to do some no decompression analysis, blah, blah, blah. So we can do the analysis on the compressed data directly, but this is a very ideal and challenging. So let's don't talk about that. Let's just say like we have compression, so we must have decompression, right? And once you have decompression, you can use the decompressed data to do the backward propagation, right? That's the idea. And you don't need to decompress data at the same time. You can progressively decompress data. When you use this layer gradient activation data, you just decompress that, and next layer you just do that, right? But what is the challenge for this work, right? Then the idea is very straightforward. Right? Compress, decompress, why this is a research publication, right? So the challenge is like because we are using lossy compression, why not use a lossless compression, right? The data has been slightly changed, but still you can control the loss. You can control the data loss, right? And in terms like overall model training loss, right? What is the relationship? Right, you introduce some error to the activation, how it would impact the overall model accuracy, the loss, right, and how you can control them. So that is the real challenging thing for this work, right? And we developed some scheme. For example, during the online we collect some parameter for analysis, and we use those like a parameter, model status, momentum, those things to control our compression configuration. And how to control that? We build some like a mathematical model. We based on the gradient value, average, or those things, and we can estimate acceptable loss can be used in the gradient. And based on this acceptable error, we reverse devise the compression configurations, and we deploy the compression with those configurations during the online training, right? And those like some formula we derive, right? So if we want to control the sigma based on the, we also have some like incremental study, right? Beyond machine learning, deep learning is not purely like a theoretical derivable. So we have some experiments, and we based on these experiments, we can calculate the sigma about the gradient loss we can tolerate, and based on this sigma, we can reversely derive the error bound we should introduce to the compression, right? And then based on the our error bound, we can enable our QSD to compress that. But also we need to modify it, because traditionally QSD can change 0 to non-zero, non-zero to 0, but this is not good for machine learning. Machine learning, you need to keep a 0, 0, non-zero, non-zero, even if it's a very small value, right? So we have modified that. And eventually, because this paper has been done 3 years, 4 years ago, I hope we can redo it or rethink it in the large language model era, right? So, but at that time we, test on some ResNet, we test on some like old model AlexNet, we test on VGG. We compare with the other state of art published, I think in the ISCA or HPC, I don't remember. They are using some hardware compressor built in the GPU, and they claim that, okay, their compressor can reduce the memory consumption, but our solution actually, you can see like we provide a highest ratio. We provide a better flexibility because we don't need to change the hardware, right? Their hardware solution needs to adapt their hardware, but always a pure compression solution, software solution. And you can see like, let's say, this is only the compression ratio, right? And you can see our no compression ratio. Yeah, this is the accuracy, sorry. This is the accuracy curve, right? You can see like without compression or without our compression, the accuracy almost the same. And this is the compression ratio, right? The compression ratio is kind of relatively stable around 10 to 12, right? It's kind of a good ratio for reduce the memory size. For example, you are using the 40 gigabytes, but without compression, you only use 4 gigabytes, right? And with those like memory reduction, you can train larger model. As I mentioned, you can train large batch size. And if you train large batch size, the problem will converge faster. Throughput would be good, right? Convergence is I think I shouldn't say it will be faster. Convergence sometimes use a large batch size, it will affect the model training. But in general, large batch size is good, right? Provide you some better performance. Okay. So this is the work. I will skip this one and finally talk about our collaboration with Meta. And I think this is kind of funny. I think the reason Meta come to us is because we have previously collaborated with the Argonne National Lab, and at Argonne there is a team developing MPI, message passing interface, and those software MPI has been widely used in HPC, right? And those group of people actually left Argonne and they joined Meta, and they are trying to help Meta to build the HPC infrastructure, AI infrastructure, right, to support their machine learning cases. So I want to share this story to you. Like HPC is not only serves the scientific computing community, even like it started from scientific computing, but now a lot of like HPC people move to industry, move to those like company because they also need to. Microsoft is also building a large scale training infrastructure, right? And their lower level thing is the same, right? The communication is the GPU programming, all these things is the same, right? So actually they come to us and they know, okay, you are developing the lossy compression. What about let's use your lossy compression to accelerate our machine learning cases, right? Especially the communication, right? Actually, these slides are not going to the detail, otherwise it will too complicated. But the idea is like, if you want to training a deep learning recommendation model for Meta to send you the news, to give you some advertisement, right? So this deep learning recommendation model, DLM, is their core business. So they rely on this model to earn money, okay? So that's why they can spend the money or they can fund us, right? Because this is their core business. So using the DLM, they train a model and based on your click, they give you some recommendation, okay? However, this model is large and this model needs to be distributedly safe on the different devices, GPUs, CPUs, node, right? Data servers. So once you need to train the model, you have to gather all the distributedly saved information together for the model training, model updates, new data, right? So let's say we conclude that in this computation problem, the major bottleneck is the O2O communication. So what is O2O communication? Let's say we have 4 people. Everyone needs to pass your information to the other 3 people. So this is O2O communication. You may think about this is the most complicated communication because everyone needs to talk to everyone, right? Need to pass your data to everyone. So O2O communication is a bottleneck in this process, and we have some like profiling results. In our cluster, this O2O communication dominates more than 60% of the time, but because our cluster is kind of slow in communication, in the real Meta infrastructure, it's kind of like a 35 to 40%, right? So even if you are using the mixed precision, if you know what is a mixed precision is that you use a 16-bit for computation, 32 for storage, right? Scientific computing is kind of like use 32 for computation, 64 for storage, right? So it's mixed precision is kind of like this way. And even with the mixed precision, the time is still very large, right? And then we are trying to use our lossy compression to reduce their communication overhead. So I'm not going to this slides, but our goal is to optimize our solution to achieve both high ratio and high throughput. Otherwise, if you only have high ratio, then throughput is low. The communication will not be reduced. If you have a low compression ratio, high throughput, the throughput is also not good, right? So we have to help them to do this. Let's forget about this detail optimization, just to take a look at this workflow we eventually will deliver. So we want to compress on the each rank, and then we are using the auto communication to send metadata, because as I mentioned, different process could have a different compressed size. And then we, based on this sent metadata, we can send the real compressed data in the tensor format. And eventually we decompress the data to use for the real training, right? The framework is not challenge, but the challenge is how we can develop, we can customize our compression for this DRM data, right? And DRM data have some different features, right? It's like vector-wise data, the frequency is extremely unbalanced, and the values in each vector is not smooth, right? Why I emphasize this? Because in scientific data, you can see the data is very smooth. For example, is a climate, is the temperature in the earth is kind of smooth, right? But this value is not smooth, so there is some challenge. Okay, and also GPU, I keep emphasizing GPU because machine learning is even emphasizes on GPU, right? Everything is done on GPU. So if you want to compress the DRM data for communication, you have to do that in the GPU, right? So the GPU also need to be changed, right? Yeah, and we have to adaptively change the error bound for different table. What is a table? So their machine learning, their recommendation system are recommended the data based on the different tables. This table, for example, let's say is for your age. This table is for maybe for your shopping behavior. This table is for what other purpose, right? So different table have different features. So you definitely need to adapt your error configuration on the different table. Right? So. Anyway, just one last slide for you to understand our current progress. And if you take a look at the original baseline and the FP16, FP32, this is the communication time I video, right? And the quantization from FP32 to FP8 and the ZFP QSC are the traditional solution, right? You can see like the QSC spend a lot of time on compression. The QZFP ratio is limited. So we want to build ours. And you can see our solution compared with the other baseline or quantization approach is good. And if you use our solution, you can reduce the time by almost 6 times. So let's say if you have 40% of the overall training spent on the communication, you reduce this 40 by 6, then it will become maybe 5 to 6% in the overall time. You can significantly improve the overall performance, right? I don't give too much detail. Sorry about that because of time limit. The accuracy is good. Okay. So anyway, this is thank you for my student for contributing all those like projects and applications. And yeah, that's it. Thank you so much for your time. Questions?
Yeah. So do you have any questions here?
So I want to.
It's okay.
Okay. So I just want to comment on this. As you can see from Dingwen's talk, so his group did a lot of real implementations. So I usually made some. Well, this is a very general comments to our own students. For example, here I know we have a lot of you guys also implement a lot with the research labs, right? But there is a key thing here what we can learn from him is how can you abstract the ideas you put in on the software development became a top conference. That is a very, very important skills. That some people spending tremendous time just develop software. And then to the end, because we all want to publish in the top places. So I think that's something is a very important skills. So I just want to, comment on this. You can see this what they're doing a great job here.
Yeah, thank you for Professor Shi for his good comment. I think also I emphasize this to my students, right? Because we are doing the system research. If you hope to spend all the time in engineering development, you can, right? But as a PhD student, publication is also important. It's good for you, for your group, for the university, right? Because the university rank everything based on the research product, right? So you have good software, that's important. But you also need to learn how to extract the idea, what is the difference from the current product and the existing product, and what is the research challenge and the engineering challenge. Sometimes is good for paper, right? So, but anyway, we can discuss offline if you want to hear some of our story, how we can change like some engineering work and add some scientific contribution to a group application.
Thank you. Any other questions?
So when you talk about frameworks, so if I understand correctly, the framework is used in the development phase, right? It's used by the HPC user to optimize their performance, right?
Yes, I think yes. For framework, we are trying to provide the flexibility for us and the users to tune, right? Which could be the good pipeline or technique or modules in the final algorithm. But eventually, if you want to generate the high-performance code, those modules could need to be deeply integrated. Let's use a GPU as an example. For example, you have let's use neural network as an example, maybe you're more familiar with that. So if you have like a convolution layer, if you have like a normalization layer, batch norm, blah, 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 and you develop this neural network. But eventually in the cuDNN, NVIDIA implemented library, those kernel need to be fused together, which means that you read the data once, you finish all the computation, and you output the data. But during the model architecture construction, you are using the Python code to construct this layer, that layer. So we call PyTorch the framework, right? But eventually, if you want to deploy those like inference code on some like a smart vehicle or those things, you have to write this in maybe high-performance C++ or CUDA code and generate the product level code, right? But for research purpose, modularization framework is kind of helpful.
So you mean in the production level, those modules will be, for example, integrated in the OS or maybe in the compiler?
Could be, yes. We integrate, for example, I haven't talked about, but we integrate some compression code. For example, let's say like a cloud migration or checkpointing software. We are not directly call our API. We have to deeply integrate those modules into the other system or software pipeline. Yeah.
So how can you ensure the optimization, like compression, will always produce the correct result, even in the corner cases? What's the general approach?
So you mean the lossy compression, right?
Yeah.
Because lossless compression always the correct because you have no information loss, right? And for lossy compression, good question. We can never guarantee 100% correctness, right? Because it depends on, for example, if you introduce an error to application, it could have like some propagation or impact of overall results, right? But we are trying to have some strategy to provide better fidelity. So that's why we call it fidelity, right? So one approach is like we can do some like error injection. For example, in security research or in resilience research, you can inject some error. You can identify what is the propagation result, and you can, based on the propagation result, build some like analytic model, prediction model, statistical model, right? And you can understand, okay, how the error would impact, right? Otherwise, if you only care about if the error just for the saving the data, will not be propagated in the application, then you only need to care about the data analysis quality, visualization, things like that. If it's okay, then we are fine. But you raise a very important question. So how we can interact with the scientists to make sure those are good things, right? So that's why we have this like $3 million project, right? We want to build like a mechanism to accelerate the loop. I give you something, you give me something. I give you something, you give me something. And then looply, we converge and find, okay, this compression is okay to use.
Great.
I've got a question on the in situ analysis. So, when I have a simulation and I run that data, right, I'm interested in both performance and compression ratio potentially,
Yes.
right? And they're probably inversely related to one another.
Yes.
But they also may change based on what the data stream actually is at a certain point, right? So,
Sorry,
so when the data changes, the time to compress it may change. So I'm wondering if any of these libraries have some sort of adaptive features that basically you can do some kind of throttling. So when I realize that the data that's coming in takes too long to compress, I can reduce the compression ratio on the fly.
Exactly. I think this is a good advanced feature. So for a large scale, long-term, like a long-time simulation, as you mentioned, right, data feature could change, right? And I think change the configuration of the compression is not a challenge. I think, but you need to pay something, right? For example, let's say we sample the data, and based on the data feature, we can quickly let's say just compress that, right? And based on the feedback, we can adjust the compression error bound or configuration on the real compression, right? And now we have like some people build like a surrogate model, right? I think the AI community people are talking about surrogates a lot, right? So you can use this surrogate or prediction. I also talk about compression prediction, right? You can based on this surrogates or prediction to quickly get some idea. Is that difficult to compress or how hard it is and what is the size, and then adjust dynamically. So this is also a branch of the research people are doing.
Yeah, excellent.
Thank you for the question.
Great. We can take one more question, if any. Yes, please.
I have a quick question about the like the prediction and also the remove data dependence during the compression. Because is that compression could be applied to all kinds of data type? Like the LiDAR data will have point data, and the video gonna have like it's based on the tab, the frame tab. So how do we remove the dependence depend on different kinds of data tab?
I think that's a good question. So in general, my answer is like, what you just described is just a different dimension of the data set, right? For example, let's say video. One video frame is a 2D data, and two frame or multiple frame is a 3D data, right? And if you gathering multiple frames together, and you can compress them at the same time, and those frames may not have like dependency, and we can use our traditional method to remove the dependency, or you can compress the frame by frame, right? Then there is dependency, you just compress the first one, second one. And I think the trade-off is like, if you gather more data, you leverage a higher dimensional information, the compression quality or ratio is better, right? So, but in general, I don't think the removing the dependency is related to the dimensionality information, 2D, 3D, 4D, it's the same. Right.
And also the point cloud data, like the LiDAR radar point cloud.
Yes, I think it should be the same, but we haven't tried point LiDAR data, but I think that's yeah, we can try.
Yeah, because LiDAR will generate lots of data and how to handle this.
Yes, exactly. I think LiDAR data is it's kind of like what I mentioned, like some instrumental data, right? For example, we have some like SKA is like universal observation data, right? So it's kind of like radio data and things like that. So and it's a high streaming data, and we just try to compress the streaming data.
Thank you.
Okay, great. With that will be all for this seminar. So let's take a